class. I'm Dr. B, your chemistry teacher. Today we are going to continue from our previous lesson. Remember that we have discussed zero order rate law. Today we are going to look at the first order rate equation. It is important that we look at that because we have series of them and they all mean different things. So today we are going to look at the first order rate law. So we look at the first order rate law. Either you call it the first order rate law or you can call it the first order rate equation. Now, we are not going to waste much time, but it's important for me to let us know that there are a lot of factors that affect kinetics of reaction. Remember that we have said before that kinetics simply explain the rate of reactions and mechanism of reaction with respect to what? To the products and reactants. Now, the orders of reaction simply explain a link between the various reactants concentration, as the case may be, and the rate at which the reaction proceeds. So today we are going to look at that. But like I said, both temperature, pressure, catalysts are factors that affect rate of reactions. But most importantly is concentration, and that is why our interest in trying to look at the orders of reaction is on concentration. Imagine that you were given an equation A giving you P, where A of course is the reactant. How do we get to talk about the first order rate law? How do we arrive at the first order rate law? Now, let us write the differential equation for the first order rate law out of this. So everything is almost the same like the zero order rate law, except that a little difference is there. But if you understand the zero order rate law, you'll be able to work on the first order rate law and the second order rate law. Now, the differential equation is simply written as the A, okay, all over what? The T, say you are differentiating with respect to time, is equals to K to the concentration of 1. But usually we do not even bother writing 1 here, because if it is not 0, 2 or 3, then it is what? 1. But for just the sake of it, let me write it. Now, at this point in time, we need to do what? We need to take the differential of T to the right hand side. So we're going to multiply both sides of the equation by minus dt. So what we're going to do here is to multiply both the right hand side and the left hand side, okay, by what? Minus dt. So if we do that, this equation will now become minus dt to the A all over the T is equals to K A1 times what? Times minus, okay, let us put it clearly, times minus the T, since we say we have to multiply in that way. Now if we do that, this is negative, cancel out a positive, so this dt cancel this. We can write this equation out, and that will give us what? That will give us the A is equals to what? Is equals to minus K the T and A1. Now remember that we are trying to look for the rate constant of this particular reaction or equation. In that case, we are expected to move the concentration of the first reactant to this other side. So it means we are going to do what? We are going to have the A all over A, like A1, of course, is equals to what? Minus K dt. Now at this point we have arrived. Remember that if it was in a zero order equation, we do not have this because this was 0. It's not considered. But because this is 1, we have to bring it in. So at this point, we are going to introduce our integration. So we're going to integrate this equation. Now, supposing this was 1, this was 2, this was 3, this was 4. So we are going to do what? We are going to integrate we are going to integrate equation what? Equation 4. So this means that we are going to introduce the integral form for dA over A, which A1 is equals to what? The integral minus k dt. That is what we are going to have. But remember that our integral from here is from A0 to A. That is A concentration of A from initial to final. And this is the time to what? T. Now, there is something very important for us to take note of from this equation, and that is introducing us a little bit to what we understand in our advanced mathematics. Now, that is what you understand in advanced mathematics is simple, is that again, but this equation can be rewritten. We can write this equation again as 1 over A times the A. I hope you know that this equation is the same thing as this equation you've seen here. So we can decide to integrate them by parts. Now, remember that the integral of 1 over x is equals to what? Is equals to ln x. That is what you know in your elementary mathematics, that the integral of 1 over x is equals to what? Ln x. That means that the integral of 1 over a should give us what? Should give us ln a. That's what it means. And then the integral of the a is 1. We have done that before. Remember that the integral of the x is 1. So if this integral of this is ln a and this is 1, it means that what we have is 1. So we can possibly rewrite this equation with respect to that. Now, the integral of k dt is simple. It is what? Minus kt, because it is only the d that will be affected. So if we bring ourselves to this side now to rewrite that equation, it means that what we are going to be having is, from the whole of this, we are going to have ln a. So we're going to have what? The ln of a minus the ln of AO is equals to what? Is equals to minus kt. This is because the ln of A is our final what? Concentration reactant, and this is the initial. So final minus initial is what represents here. Now at this point, all we need to do is to move this out this way, because we are looking for what? The concentration of the reactant, not the initial. Therefore, ln of A will be equals to minus kt plus what? The ln of AO. That is what we're going to have, because we move minus ln of what? A to this side of the equation. So it keeps us at this point. Now I want us to know that at this point is the same thing as saying y is equals to mx plus c. Then it means you can use this equation to plot your graph and also obtain your rate constant. But this is not the end for the second order rate law. So what we need to understand again in this equation is that when your normal mathematics, where you have the exponent of the ln of x, it is equals to x. Anywhere you have exponent of a value is equals to x. So if we put the exponent of ln a, it means it is a. That means the exponent of ln a is equals to a. That means that we are going to do what? Bring down this very value here. So if we link this to what we have here by placing the whole of this on top of the exponent, it means, okay, let us do it. This implies that the exponent of ln of a is equals to what? The ln of a is equal to what? The a. Therefore, we'll rewrite this equation that we have here in this format. That means it will be a being equals to what? Being equals to the exponent of the ln of a, o, minus kt. That we are going to have. You will need to rearrange this equation in order to bring this minus k this way and bring them this way. In that way, you have this very easy. Now, at this juncture that we have this, you have already arrived at the equation, but one step is left, and that step that is left is simple. What we just do there, we will say A concentration is equals to what? Equals to A 0, which is this, to the what? To the exponent of what? Minus k. The exponent of minus k. This equation now is your this is your first order rate law equation or rate equation. So this is how you can be able to derive the first order rate equation as simple as possible. So all you need to bear in mind is that the difference between the zero order and the first order is the fact that in the zero order our equation ends here, but in the second order we need a little bit of extension into what our understanding of a little bit of further mathematics to take us into what it's all about. Now at this point we can comfortably decide to do what? To do a graph of what? This first order rate equation. So the graph of the first order rate equation is always written as or drawn as this. You see, it looks very much like the zero order, and then here is the length of A, while here is the time. So it means that if you are given a question with some data and expected to check if it will be the first law or the zero order equation, you are expected to use this very equation to plot your graph. And now if you are plotting a graph of lane A against time, if it gives you this kind of a plot, then it is a first order equation. But if you are plotting ordinary concentration of reactants without the lane sign against time, it gives you this, then it is a zero order. But if it gives you a different type of graph, then it does not obey this very order of reaction. Now here of course is your lane A, which is of course your intercept, while your slope is equals to minus k, which of course defines your rate constant. I'm sure that today you have been able to acquire more knowledge or a better understanding on how you can possibly be able to derive the first order rate law from the differential rate equation. Do not forget that this class requires you to subscribe to my YouTube channel, to also follow in my Facebook page, to like, and also to comment and share. Until next time, it is